well, I see a bunch of people have joined. So we'll get started with today's webinar. So welcome. Today is a new approach to optimizing completion and stimulation fluids, the component focus mistake. So this is our third webinar in a series discussing water compatibility and other issues. You can check out our past videos on our channel or gain access through our website, and that's at interfacefluidics.com/resources. So I'm your host today, Kirk Graham, Vice President, Sales and Marketing with Interface. And as we kind of go through, we'll zip on to the next slide and take a look at our YouTube channel. You can also use that QR code if you scan that with your phone to gain access to the on-demand portions that we've already published, really looking at produced water and other water compatibility thoughts and concerns there. So I encourage you to do that. And you can gain access from our website just by going to interfacefluidics.com and clicking on resources in the upper right corner. And you'll see that news and events for future webinars, which we will be announcing early in the new year. So today, as we go through, we ask that you stay on mute and that you use the Q&A button at the bottom of the screen. That's the section that I will be monitoring as far as using that at the end for our question period. So we'll hold questions to the end, but as they come up, I encourage you to use that feature and have that listed so that we can answer your question. Today's speaker is Adam Fair, and Adam is an account manager who assists chemistry companies and E&P operators and other clients of Interface Fluidics design sets of tests to answer tough questions, often on fluid behavior. So Adam brings a thoughtful curiosity to all of his engagements, and I think you'll see that in today's session as well. So Adam, what are we covering in today's webinar?
Yeah, thanks for the intro, Kirk, and thanks for joining everybody. Today we're going to be talking about how all of the different additives really come together inside of a completion fluid. Because oftentimes we as a testing lab, we find ourselves testing individual components for their performance parameters. But today we're going to be really looking into what happens when we combine everything. Does that performance still remain the same? What are the changes like? And what really should you be looking out for when you're doing that kind of activity? So really it's about balancing. What it boils down to is balancing a dual objective of mitigating the risk of your fluids and production enhancement. So pulling those levers in a favorable way is really what we're trying to get to at the end of this conversation. And we'll touch a little bit on the topic of formulation and why sometimes there needs to be multiple ingredients inside of a completion fluid, and you can't just pump one particular ingredient in your water. Sometimes you need other things to make everything work together, right? And just for those of you who aren't familiar with Interface Fluidics, maybe this is the first time you're joining one of our webinars. We are a testing lab that we provide these types of tests as a service to the energy sector or and to chemical companies as well. And we also sell hardware to perform these types of tests inside your lab. If you're looking to bring microfluidic capabilities in-house, we can help you out with that. So our testing platform is called Sapphire Lab, and it's a microfluidic system, the center of which is microfluidic devices. And the Sapphire Lab is all of the supporting hardware that you need to make those microfluidic devices work well. We serve both unconventional and conventional markets in the context of flow through porous media studies. And we also do things like PVT testing to kind of give a more comprehensive offering. Our goal is to make testing more accessible, and not just testing in general, but a diversity of different types of tests, because really, the more tools we have in our tool belt as we're trying to de-risk these major field operations, the more data we have, the better. that's our viewpoint on that. And at Interface, we focus on a technology platform, or I guess subdiscipline called microfluidics, which is really, to put it simply, is just the study of how fluids move through extremely small channels. And it's great for isolating different fluid variables. And the content of today's webinar is a really good demonstration of our approach to that. The isolation of variables comes inside of the experimental design, and we're able to see quantitative differences in performance using microfluidics that might not necessarily be able to be evaluated otherwise without very costly equipment and infrastructure. So in the context of oil and gas, microfluidics was first used to study simple oil displacements with water, so water flooding. And you can see that example article on the right-hand side here, Ever See a Water Flood? So that's what it was all about. It was about getting visual access to understand the pore scale processes that are happening when we're doing these simple displacements. And microfluidics is used in a variety of other industries, mainly biomedical, but I'm sure many of you have encountered inkjet printers. That's kind of the most prevalent or widespread use of microfluidics in the modern day world. But other everyday items include like pregnancy tests, the COVID tests that you guys are all sadly familiar with. But in the context of the more scientific, less everyday realm, microfluidics is used in other types of applications in chemical analysis, like chromatography. And there's plenty of other examples where microfluidics has been deployed in an industrial application. But today we're here to talk about fluids, as always. And the reason for that is that, in oil and gas, I think a great deal of effort goes into ensuring the chemicals that are being purchased for operations are going to perform as desired. And we've noticed that there is a tendency to focus only on the primary performance of the selected chemical for a given application. And what I mean by that is, so for example, a surfactant, we'll look at things like IFT or the CMC, critical micelle concentration of that material. Is that enough to build a full picture of performance? It might be, but it might not be, and we'll show you some examples today. Particularly in the shale unconventionals, there's also a greater risk of damage to producing assets due to their low permeability and the possibility of a reactive shale or reactive clays within the shale. So basically, risk mitigation is a really important part of any unconventional oil recovery operation. You want to protect that producing formation because that lifespan of that well is much shorter than what the conventional markets are used to. So protecting the producing formation is paramount, and maybe even enhancing that through chemical EOR or other enhanced oil recovery methods. So today we're really going to drill down on what is holistic performance and what are good strategies to gauge that type of performance. So let's dive in. So what does performance really mean to us? Well, to put it simply, it means we're working smarter and not harder. We're putting in less effort and getting more out of the producing asset. So just minimizing the amount of cost and effort that goes into optimizing an operation or a recovery method. That's what we're all about. And like I mentioned before, one of the main mechanisms or one of the main ways to do that is to use chemical enhancement, or CEOR, chemical EOR. So when when we're talking to people, we know that there's a lot of different methodologies out there to help people understand the performance of their selected chemistries. And I've just put a couple up here as examples because a lot of times the performance of these chemistries is gauged on their physical properties. So things like a critical micelle concentration or an interfacial tension number are actually just physical properties of that material. And then you've got wet chem and bottle testing for compatibility studies that are heavily rely on visual observation, and they're not necessarily done at reservoir temperature and pressure. So how do those visual results translate to your oil production? And there are other methods out there to answer that question, like Amit-Cell and column drainage testing. It's a great method to evaluate your surfactants, but there are other challenges related to running those tests. And of course, the gold standard of all of these is, of course, the core flood, the flow through porous media testing. That's basically the top standard of performance that you can use to evaluate whatever chemical you're interested in using in the field. But within the context of unconventionals, though, core flooding can be really difficult because shale, as you know, has a very low permeability. And experimentally, or from like an experimental or engineering standpoint, from a lab perspective, running those core floods is really difficult because you need very high pressure drops and still you get very low flow rates. So doing the volumetric quantitations that you might be used to inside of a core flood become increasingly difficult. And then there's the question of fractures. In the unconventionals, of course, hydraulic fracturing is implemented. And how do you mimic that in the lab in the first place? And then how do you repeatably mimic that over time so that it's not another variable that's introducing uncertainties into your results when you're trying to pick different chemical packages or understand a specific problem? So this is an example of like a primary performance metric for surfactant. People oftentimes will compare surfactants based on their IFT values or their critical micelle concentration values. But again, like I said, usually those values are obtained in isolation, so that chemical is being tested in the absence of all of the other materials that you might be adding to a completion fluid. And it also, in many cases, if you're looking at marketing materials from different vendors, they have to pick a fluid to measure those values in. And that doesn't mean necessarily that IFT would be exactly the same in your fluid. So the first step would be then to remeasure the IFT and their critical micelle concentrations inside of the base fluid you plan to use. So that's kind of the main performance metric for a surfactant, and that's how we kind of think about each of these individual components, because the other additives that you put inside of a completion fluid are also tested with kind of that same type of tunnel vision. So for example, friction reducers and breaker pairings might be tested through regain conductivity. They might be tested through standard rheology using a viscometer. You're going to do your classic shear curves versus loading to determine what types of, how much FR you really need. And that same type of tunnel vision can be put on all other additives that you put inside of a completion fluid. So your scale inhibitors, your clay and shale inhibitors, corrosion inhibitors, they're all tested for their primary performance metrics, and typically they're done so in the absence of other materials. And at Interface, we won't necessarily be able to tell you which type of corrosion inhibitor will give you the best corrosion resistance, but we will be able to tell you, is your corrosion inhibitor interfering with the chemicals that you've put inside of the completion fluid that are intended to stimulate production? So how do we do that? Well, the first thing is recognizing that tunnel vision could be getting in the way. That's the very first thing that people need to know when they're working with these types of tests. This component focus mistake really arises when it results from tests where the additive in question is tested by itself and maybe not inside of your base fluid. So not necessarily inside of the representative water that you're using for a frac. So let's say you've tested all of those parameters even inside of your representative water in the absence of all of the other ingredients in your completion fluid, you cannot make the assumption that those types of performance metrics will carry over as you introduce complexity. So why does that happen? Well, it happens due to chemical interactions and together in the context of water chemistry. So all of the chemicals that you've now blended together have the opportunity to kind of communicate with each other and interact with each other. And sometimes that can result in a diminishment of the effectiveness of one of or many of the products. But it can also result in positive synergies that you might not have known about if you didn't test them. So this is where I'll touch on formulation and things like that. But in the same way that those chemicals can come together and bite you in, or you're shooting yourself in the foot in a way, sometimes those chemicals can come together and harmonize and work really well, increasing the relative performance of each of those materials. And that enhancement, that synergy, is the fundamental basis behind formulation, what formulation chemists do. Because even though some ingredients might seem simple, they're co-formulated to make them work better. Like as I've listed 2 examples here, something as simple as laundry detergent. We all know that laundry detergent is just a surfactant, right? Well, not necessarily. In order to make that surfactant work really well, there's other ingredients in laundry detergents like EDTA, other chelating agents that will make that surfactant work really well in hard water, for example. And now a little bit more of a relatable example, food. If you're thinking about preparing a meal and you've got all of your ingredients in front of you, eating one of those ingredients by itself might seem pretty gross, like think of table salt. But when everything comes together, it forms something far more palatable. And that's how we should really be thinking about our completion fluids when it comes to performance, and performance again in the context of oil recovery. How does it impact oil recovery? And that brings me to, I'm borrowing some terminology here from the analytical chemists, but the analytical chemist thinks about individual components in complex mixtures in this way. You've got your analyte, which is the component of the mixture that you're actually trying to study. And then you've got the matrix, which is everything that surrounds it. Now that might include other components, or it might just be the brine itself. Brine has a relatively complex composition. There's many different ions that are able to be dissolved by water. So that could be considered part of the matrix. And in this little schematic here, surfactant would be your analyte. And what happens is that when unfavorable interactions occur between your analyte and your matrix, we call that interference. And in this case, we're kind of trying to avoid any situations where that interference is actually going to result in diminished production. So how do we at Interface isolate those variables, and how do we understand those interactions? Well, we use microfluidics to isolate the fluid variables of interest. Remember, I said microfluidics is a great tool to isolate variables, and this is how we do it. The first thing we do is we have this repeatable porous media here that's supposed to be representative of the underground subsurface situation that you're dealing with. And there's three components to this chip. The first is this triangular region on the chip that's high porosity and high permeability. That's supposed to be mimicking something like proppant, right? And then you have the surrounding porous media, which has extremely tiny channels. We typically run anywhere between 80 to 120 nanometers in terms of the pore throat sizes inside of that. So that results in single-digit microdarcy permeabilities on chip. And then, of course, the third component of the chip is these serpentine channels that are used to measure the amount of oil production resulting from a specific treatment. And this entire chip is a non-reactive substrate that properly isolates those fluid-fluid interactions and informs how those chemistries will impact oil's ability to flow. So the really nice thing is that because this chip is a constant composition from test to test, and it's a new chip every time, we can manufacture this chip over and over again with the same specifications. That means you're starting from the exact same point for every single test that you run. And then the additives, that's through experimental design, we can isolate the additives as variables in the test. So what we'll do, for example, is study the additive in isolation. We typically, in the past, have used this test to evaluate surfactants. So as an example, we would run a surfactant by itself amongst a cohort of other materials. And then we would begin introducing complexity, start adding in other components of the completion fluid to understand and gauge what the difference is now that we've added this material. And throughout that process, we'll add a series of controls to be able to make those comparisons. So some examples of what this has meant in our screening programs. In this particular case, the control in this test has no chemicals at all. This is just base fluids. We typically start our projects by running a control of just base fluids. So that'll be just your frac water and formation oil to get a baseline of compatibility, get a control test to see how as we begin adding additives, the performance changes. And in this case, we can see that in our control test, there's a natural tendency of this oil and formation water to form emulsions. This image here that you're looking at on the left-hand side is an emulsion that's been captured inside of that frac tip, that triangular region. And as we begin to add chemistries, we see that those interfaces begin to clear up, and now the emulsion is no longer being able to be observed. But how does that translate to performance? Well, in this case, the control, which again is brine only, had much lower performance than with this chemistry 1 and additive 1. But the interesting thing here, and the first highlight of the chemical interactions that I'm trying to highlight today, is the difference between Chem 1 additive 1 and Chem 1 additive 2. If we look at this chart on the bottom right-hand side, everything is normalized as improvement over control, where we've actually changed the control to this Chem 1 additive 1 just for the sake of demonstration purposes. So we saw 65% less oil production from just water. So that demonstrates the efficacy of Chem 1 additive 1. But here in Chem 1 additive 2, although it did perform slightly better than brine, it's not a huge amount, and we can see that it performs quite a bit worse with the substituted additive 1 or 2. And for the purposes of this presentation, you could think of this additive 1 and additive 2 as those ingredients that you might not necessarily have selected specifically for stimulation. So this additive 1 or additive 2 might be something like a corrosion inhibitor or a clay inhibitor or a scale inhibitor, something like that could basically be interacting with the other chemicals and making sure to result in a change in performance. So again, this is just the same data, but trying to show that the different additives have quite a dramatic impact on the ability to flow back oil. So in this case, we're seeing quite a high amount of oil production for Chem 1, Additive 1, as it compares to Chemistry 1, even by itself. So another demonstration of how two chemicals together can result in diminished performance here in Chem 1, Additive 2. The next example is looking at surfactants performance by itself, and then surfactants performance in the presence of a friction-reducing polymer. So on the far left, you've got two controls. You've got the control here that's just brine, so formation water, formation oil, and then you have formation water, formation oil with friction reducer. I shouldn't say formation. The frac water. They're both frac water, and we can see here that without FR, surfactant B has the highest volume of oil flowed back. But once we introduce FR, that is no longer the case. C is now going to be the top performer in the context of a blend with friction reducer. So the next important thing to think about, so I've talked about mixtures and how the different additives can come together and cause either synergy or a diminished performance. The other component focus mistake that people oftentimes make is thinking that because they have a specific additive, they've already done all of the work. But really, concentration should be part of that evaluation as well. In this particular test, we're looking at evaluating the performance of surfactants in 91,000 ppm TDS water and comparing 0.5 GPT surfactant loadings to 1.5 GPT surfactant loadings. So each of them has a slight difference in performance when we're adjusting the loading. But to be able to cut the loading by 66%, if we look at P4, we can see that even though we've reduced the concentration of the surfactant by 66%, we still have a higher amount of oil flowed back from the flowback test than the higher concentration. So that would be the next component focus mistake, thinking that the component being present is going to do all the work. The concentrations need to be optimized for various reasons, and we can, if you want to go back to the formation damage mechanisms in unconventionals, I go into why we think that is in a little bit more depth. But that's the other takeaway that I want you guys to walk away with, is that just because you've got the component there, it doesn't mean that the work is finished. We need to optimize the concentration and make sure that whatever we're pumping down hole isn't overdosed, because then you're kind of shooting yourself in the foot. You're burning the candle at both ends, I think, is a better analogy, because you're spending on your chemicals, you're overspending on the chemicals rather, and then at the same time, you're slightly diminishing your production. So that's where concentrations come in. And really, because these types of testing programs can get quite complicated, if you begin to screen through all of the variables, you need to begin to think about which variables you actually have control over. Chemical components are where most of the control lies when it comes to our fluids. And water, most people are stuck with a given water composition for their frac and obviously for their formation water. But maybe you're looking to implement a water treatment program, or you're looking to you've got multiple water sources nearby and you're trying to pick one. Then in that case, it's a variable you have control over. It might be a good idea just to check and make sure that whatever you pick is going to be the best option. And finally, the recommended workflow for these kinds of testing programs the first step at Interface, we always recommend making sure that your base fluids aren't causing any problems, or to get that baseline performance. We recommend using just your base fluids as a control, because in our point of view, if your base fluids aren't setting you up for success, maybe there's some incompatibilities there. Those need to be addressed first before you begin looking at chemical EOR additives or other types of materials that are going to enhance your production, because you're not set up for success right from the beginning. But once that baseline performance is understood, you can begin screening your proposed changes to the fluid one variable at a time. And those variables will change depending on who you are and what your situation is. So what we typically recommend is starting with obviously your base fluids, then start adding singular additives so that you can screen a few single additives and kind of pick the best one and walk away with those top performers and begin combining them. And if you see any, if you want, like step 3, when you run the fluids package in its entirety, if you notice any incompatibilities or diminished production in comparison to what you saw from step 2, you might want to begin thinking about switching out the other top performers that you selected from your single additive screening, doing the recombination, and retesting until you get the performance that you're really looking for. And this is all, of course, in the context of the greater in the context of the greater workflow, which includes a field pilot. So there is no way to take an entire production operation and squeeze it down into a lab scale system. So you arm yourself with data at the beginning from the lab, and you validate that through other methods, ideally, like maybe a final core flood after you're done your microfluidic screenings to rule out any rock incompatibilities. You might be able to take all of those results to a reservoir engineer to do some reservoir modeling. And ultimately, you're going to end up with a field pilot, which is where the real test comes. And after that, it's a continuous cycle. So you're monitoring that performance and making changes as needed by going through this workflow. And now that you've screened all those initial variables in the beginning, you don't have necessarily as many options to pick from as you're making these changes. So the screening programs become quite a bit more simple. But in conclusion, if there's one thing that I want everyone to walk away from, it's that these individual components, when they're together, can have quite a big difference in performance than what was observed when they were tested individually. And going back to the food example here, this is some cute little GIFs from Ratatouille. You can see that he takes a bite from the cheese and he's impressed, and he takes a bite from the strawberry and he's impressed. But when he tries them together, you see he's very happy, and there's fireworks everywhere, and it's a wonderful time. But in general, just don't assume that an individual component's performance will translate to good performance in the presence of other additives, because sometimes this assumption holds true. And sometimes, even for your benefit, positive synergies can emerge where those ingredients are harmonizing together and creating something much better than either of them by themselves. And sometimes adverse impacts can happen too. So the only real way to figure all of that out is to just get some data in hand and make sure that everything's working well together. So yeah, that's it for today. And again, if you guys have any questions, you can reach out to me directly at afair@interfacefluidics.com, or you can go to our website and submit an inquiry through our Contact Us page. So
yeah, or click the little Q&A section at the bottom. We have a few questions there that have been rolling in. But Adam, thanks. Great presentation today. And yeah, of course, on the conclusion slide, having grown up on a dairy farm, anything that includes cheese just feels right to me. So, you nailed it. But no, I really liked a lot of the points you raised, and kind of like used kind of the methods can be used in a variety of different tests. And the challenges you mentioned span a lot of types of production, as well as adjacent industries dealing with subsurface complexity, whether that's geothermal and brine and CCUS and lithium extraction through brine water. Those are kind of all other areas where some of this technology has been applied before. But let's kind of go through questions. They kind of started popping in at around slide 27 or so, but I think they were kind of the main theme of the um, entire talk, right? And it might be the filtering and the tests that get there. Here, I'll ask the question, and I'm going to merge them here. But essentially, it's what's the source of the interaction? And then kind of adjacent to that, there was another question around what types of interactions cause the damage in the behavior, right? So it's really around that, what's kicking off that interaction.
Yeah, so there's a lot of different things going on in those complex mixtures, but really when we see these changes in performance emerge as multiple ingredients come together, you start to see the impacts of what are called intermolecular interactions. So those could be broken down into multiple different categories, like your electrostatics and dipole-dipole interactions, van der Waals and London dispersion forces, et cetera, et cetera. Those classic things from the general chemistry textbook of intermolecular interactions. That is what's governing what you see in terms of behavior. In terms of damage specifically, that would just be resulting from an unfavorable interaction, right? Because I mentioned that you can also have favorable interactions. So the damage is coming from the interactions that are not favorable in this case.
Excellent. That's great. And we will be recording, we have recorded the webinar. We'll be posting it online on YouTube as well. And there have been a few questions too about some of the sources that we listed as well. So we'll assist you in answering those offline as well. Any final comments before we go today, Adam?
Nope. Just thanks for tuning in today, and I'm happy to chat questions and answers offline individually. So, like I said, I'll just quickly put my contact information up here one more time.
Yeah, that's great. And Adam, thanks again. We look forward to hearing what's next for you and what topic you'll discuss in 2025. But this 2024 water webinar series was a resounding success and a lot of interest, and I think really helpful information for people. And that makes me think of additional resources available from our resources section on our website, like the water quality matrix. That came out early in this series as kind of a supporting document that I think was really helpful, especially for engineers that where it may not be their pure domain expertise, but gives them something, equips them with something to be a little more dangerous in their questioning. And really think that's a valuable resource as well. So thanks for all the effort it took you to pull this together and to present. Sincerely appreciated, I'm sure, by the audience as well. And of course, reach out to Adam, reach out to Interface Fluidics if you have any questions. And thanks again for the great questions that you did present today. Thanks again, everyone, and we'll look forward to seeing you soon.